Hello to everybody. Welcome to IDEA StatiCa webinar. It is a release webinar on the version 8.2, focused on what we have in concrete. We did a similar webinar yesterday on steel connection design. Of course, the recording is on the website. And today we will take a closer look on what we can do in concrete details. We are using GoToWebinar. You are all muted. Please check your audio settings on the right in the ribbon and feel free to input any questions using the chat window. My name is Juraj Sabatka. I'm responsible for sales and support at IDEA StatiCa. I have two of my colleagues here today, Philip and Lukáš, our product engineers. We will show a little bit of theory, a little bit of workflows, and practical live examples from engineering practice about non-standard concrete details. And it is really about trying to do something new, to do structural design and code check of non-standard beams, non-standard walls, other concrete details, which, for example, is a beam with an opening, with a depth end combined. Theory behind this is the discontinuity regions, the regions in concrete members that cannot be described and analyzed by the standard equations. Similarly, in walls, to properly analyze how the stress is redistributed and provide a clear code check. This also has use in the prefabricated industry and also in the bridge industry, when we can analyze diaphragms, complex cross sections, cross beams. We prepared two examples, but before that, we want to describe a little bit of the assumptions. Philip, please go ahead.
Okay, thank you, Juraj. So my part will be about the solution which we implemented. So firstly, let me summarize what do you have in current market. So the first method which we can use is a so-called strat and tie method, which is quite simple and well-known method. It's also used in Eurocode for shear checks, but it has a lot of oversimplifications, and it's kind of conservative in a matter of the resistance. There are also more disadvantages. I will talk about them later in next slide, but mostly the first one is that you are able to check just the ULS. On the other hand, you have scientifically oriented programs like ANSYS, MIDASPHERE, and so on. There are many more, and they are trying to simulate the reality, right? So you get some virtual reality with the average crack width, not the code checks, and you really must be an expert to know the material models, to do the meshing and so on, and it takes you weeks to compose such a model. And the next solution, which we are trying to present you, is IDEA StatiCa Detail. And we are trying to combine the easy workflow of strat and tie method with the outputs on the level of the scientific ones. And we can provide with safe and economical design at the same time. So as I spoke about the strat and tie method, the usual disadvantage is that for the same model, like in this case some wall with the opening, you need to work with many models to capture the real failure of some specific detail, right? And this is a disadvantage. In IDEA StatiCa Detail, you can work just with one model. We can also provide you with the reinforcement design. As we can do any shape and any topology, you really can step out of the predefined or the examples from literature. And to do that, we developed few tools which we'll present, and one of them is so-called topology optimization. You can see the results on the right part for the effective volumes. This means that for each effective volume of the structure, we can show you the most effective position and direction of reinforcement. I'll speak detailedly later. And for the ULS, on the left side, you can see some basic overview what's happening in the structure and the governing check and the biggest point of the detail. And of course, by this method, we are also able to provide you with the SLS checks later. All of these parts in structure can be visualized detailedly, so you can see the stresses and anchorage bonds in each rebar or in the concrete as well. And we said that we can give you detailed results up to 15 minutes when you are doing it from scratch. So to speed up your process, we prepared a few templates which we can show you, and many more will come. And of course, you can do some general input to make any topology you like. So we do it to have a general solution for a wide range of users. A little bit of theory, what's implemented in the software. So as we said, it's a code-independent method, but at the same time, it complies to the code because we use the material diagrams or stress-strain relationships which are provided by it. So the blue line is the code, is the one which code gives us, but we use the modified compression field theory, and we decrease the resistance, compressive resistance of concrete based on tensile strains, right? So the red one is actually a reduced one, which we use. I will show it later in the software, but I want you to remember this. And also, there is no resistance in tension, right? So the tensile concrete is neglected. By this, we assume that the concrete is cracked, thus all the tensile strains are bared by so-called tension core model, and we use an embedment for each rebar in the concrete, right? So you can see it by the red diagram. It's represented for tension stiffening. As we are speaking about this and why we implemented such advanced things, is that we want to comply not with just the static but also to kinematic formula, and thus we can capture the real mode of failure to solve ductility examples. And of course, this enables us to do the SLS checks. A little bit about the tension core model, how it's connected to the concrete. We developed a bond model or the anchorage model, which this is just the model how it works. So the concrete is connected to the reinforcement by special finite elements with the springs in the end, and this enables us to give you results about the anchorage force, total force along the length, and also the bond stresses. I will speak also about it later. As it's finite elements, you need to verify and validate, and we work closely with the ETH University in Zurich, which we see as one of the world leading experts in that area. And they are responsible for material models, verification and validation, while we do and develop the software itself and all the numerical methods inside. They verify due to some live tests which were done previously and are well described in the literature. You can see the list on the right side, and many more are presented. We just don't have that so big slide and don't want to bother you with a huge list. And also they are validating with their live tests and also against other softwares, like in this case it was Athena. Maybe some of you know it. So there was a brief overview and assumptions used in a software. Let's switch to the live examples. And the first one which we'll present is depth and with an opening. So let me switch to the software itself, right? It's called IDEA StatiCa Detail, and I will run a new project which will load a wizard, which helps us to input everything. It remembers my last input, so I can select the specific concrete grade, the grade of the reinforcement, which will load the material properties based by code. Automatically, I can adjust the concrete cover. It's just the default value. I can change it later. So let me just go briefly. When I click on specific topology, more templates will come out, as you can see, and many more will be added. So let me start with the depth end from the one cross section, which will load one member, one depth end, and point support in a few seconds. Right, so I will stick to the default cross section, but you can use any from our library, or you can adjust it with the values. And let me show to you that the one which we input is automatically transferred or discretized to this gray one because we are making a 2D model and we need the width for a stiffness of each finite element. Why do we do this? Is when I go and switch it to, let's say, 100 or 1000, this is not stiff as you would assume. It would be infinite, but we take some coacting or coacting width of the slab. So let me switch back to 450 millimeters, and we'll adjust the geometry a little bit. So let's say I will do a haunch on the depth end, right? So it's another possibility. So for 45 degrees, I will use this value, and I can also introduce any other part of the model. So let's say next member, another depth and more openings, as I will add one. Also another supports or line supports. They will be shown in next example. I can hang the beam in some construction stage. Also, I can hang it by some patch supports. So basically to hang by some rebar in the model and many more. For instance, some bearing plates for transfer of loads. So let me go for an opening, a circular one with a diameter of 0.5 meter. And to adjust the position easily, we have so-called master and insert points. So I will adjust the position by the master point 8 of the member and by the 8-point insert point of the opening. And now I will specify the distance between them, so 1.5 meter, and you can see it in the picture that it's given here. So you can easily input the correct position. Now the software warns you that this trimmed end is very close to the last source of discontinuity. In this case, we combine 3 types of discontinuities. The first one is the support area, second one is the haunch, and the third one is the very close opening and quite big, let's say. and the red highlight warns you which ones are the ones causing its insufficient length. And we say that the trimmed end should be at least 1.5 times the height from the end of the last source of discontinuity, in this case the opening. So I calculated like 4.6 meters, and now you can see that the warnings disappeared and the model is correct. As the navigator guides us, we can go for the loads. As one load case has been loaded already, it will be the permanent type. And let's go to input some internal forces. So the section about the support has been generated, and to introduce the reaction I will use 100 kilonewtons of shear force. You can see that right here. Let me also delete the load impulse to show you. If I introduce just the reaction, it will be constant, and the bending moment is just the reaction times the lever arm. And to introduce the reduction of shear force and the parabolic bending moment diagram, I will apply the line load, right? So like this, and let's say it will be -10. I can give any value, or trapezoidal forces. Also, let's make another one which will be variable, and this will be mentioned also later. It will enable us to differentiate between the permanent and variable load cases for the crack width and proper assignment of the forces, right? So another reaction from the variable load case is in -12. And of course, we will combine these two, and let me specify the partial factors. So 1.35 for a permanent, 1.5 for a variable load case. And this check button means that I can specify which load cases or combinations will be considered in check. So let's say I want to check just this combination. As we define the geometry and we load it, we can proceed to reinforcement. Let's say I don't know how to reinforce it, although you see that some template has been loaded. I have two options when I come to reinforcement, because I landed in Design Tools tab, and I can run the linear analysis, which is quite quick. Let me just show you some filtered option, right? So you can see the areas with values higher than given value, and you can see which parts are under compression, which parts or which elements gives us the most tensile areas, and you see which ones to reinforce, right? So you can see some beam behavior here, right? So banded, so compression up top and the tension on the bottom fibers. And the second possibility is the topology optimization, which I mentioned in the PowerPoint presentation, and it calculates it for default for the four effective volumes, 20, 40, 60, and 80% of the structure, and it finds the minimum of the energy for the ductility of the model, or it's the most stiff model for a given ratio of effective volume, right? So if you want to use just the 20% of structure, this is how it would look like. And you see that, as we have seen, the big tensile areas were about this edge or intersection of edges, and also at the bottom of this opening, and the most effective reinforcement would cover them both like this. Also, there is one more tie, let's say, but it does not have so big force, so it's quite light color. If I have these results, I can go for an input of reinforcement, and these results will be presented with lighter colors, and I can input the reinforcement, and I can see if I comply with it. In this case, I will switch it off, but you can feel free to use it anytime. As I used predefined template, some basic reinforcement for these types has been loaded. And so let me show you what else we can add, because for instance, I added the opening to the template, so it does not have a reinforcement. So let me go briefly through the reinforcement types or items. We can specify the layers of bars, or some bent arm bars, inclined ones, or some, let's say, cages. So as the stirrups which are here, I will show how to adjust them, or some cage around the opening. So let me select it. I will decrease the number of layers to 2, and also for the diagonal ones, I can elongate it and so on, like this, I think. And you can see directly here how it's modified. It's quite simple and easy. Let me go back to stirrups operation, and I will switch to the 3D model. It's just the rendered one, but I will show you some features. I can specify the diameter, so it will be the 10 millimeter of diameter, and of course I can specify the number of branches, right? So you can see added link here if I switch to 3 latched stirrup. Also, I can select the specific end type. I will use the overlap, but you can see it here better in a 3D window, although all the positions are easily or easier inputted for a 2D model. So let me show you how to specify the distances easily. So I can specify it like with absolute values, and you can see how it's placed here. Or I can specify the first and then say 5 times 150 millimeters, and you can see what has been done. Or, for instance, I can say I can go for 2.5 meters and make 17 distances, right? Or I can go like fill in the rest by 200 millimeters. It's all set in the tooltip, as you can see. Okay, so that's for stirrups. Let's go to the next operation, which is the group of bars. It is the first one which I showed you, and we can specify the different diameter, the number of bars in layer, right? So I can show it to, again, in a 3D. I will select and make 3 bars in layer as easily as it can be. Now, for the anchoring model, bond model, which I mentioned, is that I can specify the different end types. Yes, so they are sorted from the least stiff to the most stiff type of end type, and they are all based on the code. So basic anchorage, then I can do some bending, hooks, the loops. It can be also welded. It has its own mark. Or as I shown you, as I can show you here in the end, it can be so-called continuous bar, which we assume that it will be fully anchored on a given value next in the beam, right? So it continues to the rest of the beam. Let me also show you how to do an inclined bar, and I will use some reference by a group of bars. Maybe you will be curious why I would do that, but I can specify the definition of bar by more edges, right? And now the edges numbers have been loaded, and I want to specify it by the edge number 4, 6, and 1. So I will just type it in the correct order, and you can see what has been defined. And I will shorten it a little bit, right? Like this. And also I will make it diameter number 18 and 2 bars in a layer like this. Okay, so let's say I reinforce the model, and all that needs to be done is to get it checked. So I will run the nonlinear analysis, which basically means, as I mentioned, we differentiate between the permanent and variable loads. That at first we will load the model with the permanent load case, calculate the stress level, and then apply the increments of the variable load, right? And this is how the calculation is done. And after a few iterations, we will get the results in a very nice way, which we will explain. So it plastifies now a little bit, but in a few seconds we will get the results. In the meantime, let me just mention that you can feel free to ask the questions. We will go through them in the end, right? So we have the results, and this is how we present them. As the legend tells you, this arrow shows you the most critical or governing check, right? So this is the extreme part of the structure, and the blue reinforcements are the ones in tension. The thicker the line is, the bigger force is in it, and the darker the color is, it has a bigger level of stress in it. And once it reaches the yield point in diagram, it's presented with this hatch. Also, as we introduce the anchor model, you can see here that if we reach near the limit of the bone model, we use the yellow hatch to show these areas. Also, as we can show you the rebars in compression, they are the purple ones. So you have real an info about the real behavior of the structure and everything in it. Let me also specify the bigger filter for compression fields. And if you are familiar with the strut and tie method, you know that these are so-called struts, right? And this would be a tie. So what is problem in this area, node area, would be that there is also a strut and also a tie. And as I mentioned, we can see that it's decreased. The compressing strength is decreased in that area, and we can see that it's decreased by the 77 to up to 77% of the compression strength. We can also see the utilization in stresses, all the stresses in principal directions, so principal tension and compression, also the strains, right? And as I mentioned, the Kc factor for the reduction. I will switch to the reinforcement, and I can see, for instance, the stresses in each rebar, right, along the length. So let me go, for instance, for the stirrups or for the cage around the opening. I can see the strains, or I want to see the anchorage and the bone model. So for instance, I want to see the total force along each rebar. So you can see, as I mentioned, this is enabled or allowed by the bone model and the springs in the end of each rebar. Also, we can provide you with some auxiliary tab, as we will introduce the SLS checks just in the version 9.0. So we call it now like auxiliary, and this is some basic overview where the cracks could appear. It's now based just on an excessive tensile strain, but later it will be a real code check on W for W limited value, and also the deflections, right? So deformed shape, we also need to adjust. Now it bends like upwards, but it's the real one, and this is just the reference point. Okay, so you have now a clue how the results can look like. You can see everything there, and you usually need to see some output. So the first one would be a bill of material. So we prepared a table with all the information about the material used in a model, each shape of each rebar. And in the end, there is also an overview table. For instance, usually you want to see parametric usage of reinforcement to ratio. Or you want to see all of these results and bill of material in a report. And you can see that all the informations which you used in the model are here. So the specific code values for the materials, used cross sections, the geometry which you used, the loads, some scheme of reinforcement, and also the stress flow overview which you have seen and we explained, and all the detailed results, including bill of material. Right, so this was the first example, and let me switch the presenter to my colleague Lukáš, and he will show some example of prefabricated wall like this. So Lukáš, it's yours.
Okay, thank you, Philip. I hope that you will see my screen now. I start with a new project in detail. And at first I need to set the grade of the concrete or strength of the concrete, which will be C30/37, the reinforcement, and the cover. The cover, I can let it for the demonstration like default, and I switch on the templates walls and subtype walls with the opening and the door. Okay, now we can see, now we can see default geometry with default length and height and default operations. What I will do, I just only edit the opening for the door. I need to move the opening about half meter to the right. Yes, so just edit, and you can see the door has been moved to the right. Okay, now I would like to have only only two line supports. So let's remove this one. So I remove that, and only edit this length for the half meter. You can see we have defined the line supports like this one. I switch to the model, and I have done with the geometry, and I can immediately go to the loads. Now you can see the first load case has been appeared or is set like default. This is type permanent. I can let this for the purpose of the demonstration, and only create the second load case, which will be variable. For the variable loads, I need to input load impulse. So I edit. The impulse will be like line loads. With the intensity minus 15 kilonewton per meter on the top side of the wall. Okay, so I have done, and now I need to create a nonlinear combination. The nonlinear combination is composed from these both load cases, and here is a combination rule for that, and I only edit the partial factors for the permanent loads will be 1.35, and for the variable loads load case can be 1.5, as Philip mentioned. Okay, now we have prepared loads like combination and load cases, and we can proceed to the reinforcement. In the reinforcement, we can see our wall with the reinforcement, and at first we need to run a linear analysis. It's very quickly process, and we can see the compressive fields and tensile fields. If I switch over the nonlinear combination, for the nonlinear combination, you can see the struts and ties. Yes. Okay. Now I will run a topology optimization. it's iterative process. It will be quickly. Okay, and now we can see very impressive shape of the arch or of the stress fields, and tensile fields for the effective volume of 20%. I'll switch over to the 40%, and we can see another redistribution of the tensile fields and stress fields around the opening. Okay, now I switch on to the mode, to the button Infuse or Edit, and we can see the fields for the compress and fields for the tensile stress and the reinforcement. And according this field, I can make some adjustment or editation of the bars. I will start with the group of bars 2. This is this one, and I would like only elongate these bars to the top edge. So you can see if I switch on the checkbox, the bars is elongated. Okay, so we have done with this reinforcement, and let's move to the inclination bar. The inclination bar, I would like to elongate this inclination bar here, so only change the length for 2000 millimeters, and I would like to change the angle of the inclination bar, so only overwrite this value or this angle. You can see we have done with that, and we can go to the check and run nonlinear analysis. During this process is calculated or are calculated load cases and one nonlinear combination. It will be very fast process because we have only one nonlinear combination and 2 load cases. Okay. And now we can see a summary overview for of all checks, like for the concrete, for the reinforcement and the anchorage strength. And we can see the item which is most utilized due to this check. Okay, I will switch over I'll switch on the traffic lights, where we can see for the separate or for each material like concrete or reinforcement, we can see the utilization. We can scale it to see the range of the acting utilization, and for the separate materials, we can see the utilization. Okay, in the bottom part, we can see the summary of the reactions and the applied loads and equilibrium for that. Yes, now I will continue to strength. We can see the redistribution of the principal stress or utilization. I will start with the principal tensile strength and principal compressed strength, and we can see the struts and the redistribution of the stress and the utilization. Yes, if I switch on the reinforcement, we can see the stress for each bars or for each component from the reinforcement. For example, this is inclination bar and here we can see the values like utilization and the ratio between the stress in the bar and the design design value or yield point of the reinforcement. Okay. Now let's move to the anchorage, and in the anchorage we can see bond stress on the bar and the utilization. This is very important value, like this, and the other parameters which are placed in the tab. For example, relative displacement on the surface of the bar. Okay. And now let's move to the last tab, auxiliary, where we can see what part, or we can see the map of the areas which where are correct permissible or inadmissible. Yes, and deformed shaped in the Z direction, X direction, and rotation. Now I have showed to you how checked a prefabricated wall in our application detail, and I will switch over my presenter to Juraj.
Thank you very much, Lukáš. So these were the examples. Let me check the questions. We have several of them coming in. Before we sort them out, this software is live. It's out there. It's for you to test. From the experience so far, you can get a very good feeling about it after 30 minutes of testing. You can try to model standard concrete details. You know the results for you, so you can compare, as well as the non-standard ones, the complex ones. So it's up for you to give it a try. Before we go to questions, right after the webinar, please fill out a short survey how you liked it, and if you want the trial to be sent to you, we will process the recording and send it no later in 3 days to let you go through it. We also have a release note on the website with a full description of the features. Okay, looking at the question, we have similar questions about DXF export. Basically, if we can start the process using existing DXF file. Philip, can you get that?
Yeah, I'll try my best. So let me switch to detail. I will run the new project so we have a clear. Okay, so as I mentioned, we have some general input. So let me show to you how to import, for instance, geometry. There is a import DXF button. Let me just find some, okay, DXF. And now this DXF is composed of lines. Of course, it can be polylines and so on. So I'll just make an outline out of it. And this shape you can see transferred automatically here. All I need to do, as it was a 2D DXF, to adjust its thickness. Also, we have a possibility to combine these approaches, so I can use the template and use DXF for the reinforcement. There is also import DXF button. So let me see some file for it, like this. And for instance, I will show it to you on, I don't know, on 2 bars, maybe, like this. And you can see that if I switch here, it's also like 2D, so I need to specify how many bars in transversal direction I want to use, right? So like this. It's not a problem to give it any shape and also to edit the ending if I want, but usually I have drawings with it. Also, when I look on the questions, I will answer one more because you ask about these small arrows. So for instance, I will use the bearing plate for it. and I specified the edge number 3. You asked for this orange arrow, which represents the positive direction when you apply something, right? So now you can see that you applied from the beginning in that direction. So there is the beginning, right? Also, the same applies for the reinforcement. It shows the top or the origin. Okay.
All right, great, Philip. And let's we are getting close to the end of the webinar. Let's do one more question. Are you using bricks or 2D elements behind this?
Okay, I will try to answer that as well. Although we use few things from the 3D positions, we use 2D finite element model. Like I showed in a depth and example, it's represented by its midplane. But as for the embedment, we calculate it from the position of the rebar in a cross section. It means we calculate also the influence of near edge for each rebar, right? But in the end, it's based on the overall area of reinforcement in a longitudinal section.
All right, thanks, Philip. Questions we did not cover now, we will cover over an email. We'll review what's arrived and get in touch with each one of you. Thank you very much for the attention. Thank you very much for taking time of your day, and we'll be looking forward to work with you on this more in the future. Thanks again, and bye-bye.
Have a nice day.
Bye-bye.